Okay. Oh, thanks, Luke, for the nice organization, and also for the DSI for the kind invitation and organization of this event. I apologize for switching the order between G and two speakers. So I'm Yulong Lu. I'm from the math department. I'm applying mathematician working on various aspects of AIs and machine learning. So nowadays, general AI has produced many advancements in many different tasks, like natural language processing and also scientific discovery. But oftentimes they are used as a black box, and there's lack of rigorous understanding of those models. So there are several key challenges I want to bring up. First, how to quantify their theoretical guarantees in various tasks, and what are the capabilities and limitations of those models. Can we somehow simply use the general AI models designed for languages to scientific discovery? Do we need to kind of modify the models in a way that it's better fit to different scientific tasks? And how to design the models to promote more better generalization and efficiency. So in the past few years, what we have been doing is to kind of prove some rigorous guarantees for this two kind of general AI models that underlie many different applications. One is diffusion model, and the other is called transformer-based foundation models. My second major span of research is to design new general AI models with pro guarantees for accelerating large-scale scientific computing, especially for solving complex PDEs. So I will show you some examples where we have used the general AI for. So for regarding diffusion models, we have used the models to kind of upscale the low resolution data to high resolution data. And those data can be fluid dynamics and turbulent flows. So on the left panel, you see that there's coarse grid solvers. The simulation comes from coarse grid solvers. You can use diffusion models to actually get high fidelity data from this low resolution data. On the right, you see another example of Euler equation where you can you can grow those fine scaled shocks from the low resolution data as well. And another research we've been doing on general AI is to understand the mathematics of transformers, in particular in the context of incontinence learning. We have seen many applications of this incontinence learning for learning dynamical systems, learning complex PDEs, and how to actually get theoretical guarantees for those things, and how to understand the also limitations of those models as well. We have two papers about the theoretical aspects of this. Some collaborative directions I come up with. So one regarding the score-based diffusion models. Can we design the efficient models for accelerating the sampling of multimodal distributions arising from computational chemistry and material sciences? So, for example, how to use diffusion models to find new materials, mainly finding atomic structures, or transition path sampling, for example, from particular dynamical simulation. How to design score-based filtering methods for data simulation. So that's very important for weather forecasting. And regarding transformers or foundation models, so one direction that I find very interesting is so scientific data are different from the text languages because they're not that compressible as text. So one important issue is we're not going to use a foundation model to actually deal with very high dimensional data, the scientific data. How to build a physical informed dimension reduction for those scientific data, so they can use this use a foundation model to actually do a generalization on the latent space. And another aspect of foundation model is to kind of design a data reduction strategy to scale up this foundation models, which really require massive data sets and training tasks. And can we design some kind of data reduction strategies to achieve almost optimal generalization with minimum number of data? So that's a few directions I'm interested in, and any questions?
Can you go to the two slides before? Yeah, oh, this one. Are they two different? You're showing two sets of results, right? Is it two different sets of results?
Yeah, so the left panel, left side is for the turbulent flows, the Navier-Stokes equation, and the right-hand side is for Euler equation.
See,
where you see a lot of shocks.
Reference and so the direct is the original.
Direct is from the Causeway solver, so it's like a low resolution data, and the right reference is for the high resolution data, and this middle one is the one that we generated using diffusion model.
I see.
You see these two things are very similar, and you see a lot of fine scale structures that grow up from these diffusion models from the low resolution.
That. And on the next slide, you have an impressive, on the next slide. Oh, yeah, this one. I think you have a pretty impressive set of question that you're pursuing. Are you looking at specific applications?
Yeah, so first one, I think so these applications are for accelerating the sampling process for material science or MD simulation. I think some of the audience are doing similar things. Chris has been working on material science applications and using diffusion model for that. Some people for transition paths. I think I want to know more about those things from you guys and potentially design new methods for this. The other thing is for data assimilation, which is different basic inference problems, is that it's dynamical problem, but similar ideas can apply for those problems.
Would it make sense to do something like this across multiple domain areas?
Yeah, so for time series, so especially for the thing I've been doing with incremental linear transformers for dynamical systems. So I've been chatting with Sungjin today and some other people. He has been doing this for traffic flows. Potentially, it can be applied for other flows as well. So I'm from math, so I want to understand those methods from a fundamental perspective, and perhaps design new models with better guarantees.
May I ask one question? So diffusion models are very popular and it's a great choice. But did you consider other models for generative AI, such as normalizing flows, which may have some nicer mathematical properties?
Yeah, so I personally haven't done anything on normalizing flow, but I know that pretty well. So I nowadays we see many performance guarantees from diffusion models that somehow beats the performance of normalization flows. I wouldn't say we shouldn't look at normalization flows, but I would say diffusion models tends to have better properties in many applications. So that's the reason I focus on those things.
To follow up on Shashi's work, there's this stochastic interpolance framework that I think goes
flow matching. Yes, there's ODE based models and yes, so that's why I'm emphasizing score-based models. So because score itself is a mathematical concept or statistical concept, but it's assimilating all the information from the data. But if you use ODE models, the concept is called velocity. That stores information from the data. But store has a lot of other properties that mathematical properties. I think it's useful and for applications. But certainly we can apply for ODE-based models. But at the moment, I think this will be enough for me to study those things already. So